Hello, so welcome back to another class. Today we will be discussing about the application of derivatives of vector valued functions. So what we will see today is something that we already have an idea, but we'll just be giving, we'll just reinterpret the idea that you already had done in your lower semesters. We are going to interpret it in the form of vectors. So it is about curves, tangent, normal, arc length, and curvature. So if you remember a curve, okay, let us first think about it in two dimensions. So maybe you are having a curve that looks something like this. Okay, so what will be you are given any point on the curve, and then this one will be the tangent. Okay, something that looks like this. It will be a tangent. The normal will be a line, okay, which is perpendicular to the tangent, and then arc length, okay, if you are saying something about an arc length, then maybe if you have any 2 points AB on the curve, then the length of this curve from A to B, it is called the arc length. Okay, and curvature, it measures how much the curve, okay, how much does it really curve. Okay, just like a straight line. Okay, so it's not curving at all. Okay, whereas if you are having a curve, we have something to measure how much it curves. We will measure it by using the curvature. Okay, so again, we can interpret this one in 3 dimensions. Okay, it will be the same thing. It's just that the curve, it is present in a, you will also be having another axis, x, y, and z axis. Okay, but again, let us have a better idea of what a curve is. Okay, so we can just draw anything, okay, and then we can just say that this is a curve. Okay, but if we have to define it, how will we do it? Okay, okay, a curve. Okay, if we are going to view a curve, again, let us try to view it first in 2 dimensions. Okay, so because we are using only 2 dimensions, so let us see. You can imagine something like this. Okay, the curve, maybe it is starting from the origin. Okay, it can start from anywhere. Okay, but let us just say that it is starting from the origin. A particle is starting from the origin. It is moving. If that particle is moving, of course, it will trace out a curve. Okay, so because it is starting from the origin, t equal to 0, the particle is at 0. Okay, the coordinates is 0, 0. Okay, because let us think that after 1 second, okay, let the particle be at 1, 1. Okay, after 1 second it will be at a point 1, 1. Okay, we can just think of it in this way. T equal to, maybe the particle is at 2, 4. Okay, maybe somewhere over here, 2, 4. Okay, if it continues like this, t equal to 3, then the particle is at 3, 9. Okay, you can easily plot it. Okay, similarly for other times, t equal to 4, t equal to 5, and other case. If you go by this data, then what we can do is we can even measure, we can even find the position of the particle when the time is half a second. Okay, we are doing it for 0, 1, but we can also find the position of the particle at half a second. Similarly, 1 by 3 of a second, 0.1 second, and so on. Okay, so if you go by this data, what we are having, it seems that the particle is traveling in this way. Okay, something like this. Okay, it is not exactly moving in the straight line. Okay, there is some curve to it. Okay, so what can we actually do? We can write the x coordinate in terms of t, and we can also write the y coordinate in terms of t. So if you have to describe this curve, you can describe it in terms of the time. So the curve, we can simply write it as t square. Okay, how did I know that it will be this one? Because just say if t is 0, will be 0, 0, t and t square. 1 and 1, 1 square is 1. Okay, 2, 2 and 4, t and t square again. 3, 3 and 9, t and t square. Okay, so what we are actually doing is we are interpreting the curve in terms of time. This is actually what we will do. So time, it is a parameter. We have described the curve in terms of the parameter t. Okay, so what we will do, okay, we'll write it down. Parameterization of a curve. Okay, what we can do is we can simply write it down. The curve, this one is when it is in 2 dimensions. Similarly, we can do it when the curve is in 3 dimensions. So what we can do, we can simply write the curve as something like this. We can write it as f1t, f2t, and f3t. Okay, this one is in 3 dimensions, this one is in 2 dimensions. Okay, for example, over here, f1t, it is a function of time, so will be t, f2t will be t squared, and f3t, okay, we are not considering f3t over here because it is in 2 dimensions. Okay, so this one is a parameterization of a curve in 3 dimensions. Okay, curve equal f1t, f2t, f3t, where t is a parameter. Again, just like I say, you can just think of t as a time. Okay, it may not be the time, but you can just think of it as time. Okay, so but because we are going to interpret it in the form of vectors, so we will need something that is called a position vector. Just imagine something like this. Okay, again, we are going to do it first in 2D. So maybe this curve, it is given as f1t, f2t. Okay, so the position vector at any time t, because it is depending upon the time t, so we can write it as rt. We can write it as f1ti plus f2tj plus f3tk. Okay, I will give an example. Okay, example, if the curve is, this one is just an example, if the curve is, okay, maybe t square and sine t, then rt will be ti plus t square j plus sine tk. Okay, so we'll look something like this. This is the position vector of the particle at any point t. Okay, since now we are interested in the tangent vector, again over here I will just give a very brief explanation. Okay, but a more detailed explanation will be given in other videos. Right now I just want you to know how to calculate the tangent vector, the normal vector, similarly arc length and curvature. Okay, the details of the explanation will be dealt with in another video. Okay, so over here what will we be having? We will be having something that looks like this, tangent vector. Okay, again I repeat, if this is a curve, then the tangent vector at this point, okay, it will look something like this. Okay, we'll have an arrow and will point and it will be tangential to the curve. If we have to find this vector, we can easily do it. just by differentiating this position vector. Okay, tangent vector r dash t. Okay, we just differentiate this vector where, okay, just to be more clear, I will write it like this: r dash t, this ddt. Okay, just differentiate this one, you will be having the tangent vector. If you are having the tangent vector, you can also have the unit tangent vector. Okay, it will be a tangent vector which has unit length. So we have a special notation for this one, which is t. Again, everything depends upon the time, upon the parameter t. Okay, it will be unit tangent vector, so we will just divide the tangent vector by its magnitude. Okay, so this one will be the unit tangent vector. What about the normal vector? Okay, I will just write down the unit normal vector. The unit normal vector, again we have a special notation for this one. It is denoted by nt. It is equal to differentiate t, okay, differentiate the unit tangent vector and divide it by its magnitude. Okay, and then we will also have this one, the arc length. The arc length from A to B, from t equal A to t equal to B, is given by this formula: A to B r dash t dt. We just integrate this tangent vector, this magnitude. Okay, I will give a brief explanation for this one. How do we get this formula? Okay, so over here what we are doing, okay, suppose at t equal to A, okay, this one is the curve. When the time is equal to A seconds, maybe the particle is over here. When the time is equal to B seconds, maybe the particle is over here. We want to find the length from A to B, okay, the arc length from A to B. We are measuring the length of this curve from A to B, and it is given by this formula. If you remember, integration is just an infinite sum. Okay, we have learned that one. Integration is an infinite sum. It's a limit of an infinite sum. So it's like we are just dividing this curve into many straight lines. Okay, very, very small straight lines. Okay, if you are dividing it into small straight lines, these small straight lines, they behave as tangents, right? These small straight lines, they behave as tangents. Okay, so the length of each small tangent, if you add it, okay, you will get the length of this curve. So that is what we are doing over here. We are just finding the length of each tangent, very, very, very small tangents. Okay, and then we integrate it from A to B. That is, we are just finding the sum of all these tangents. Again, I repeat, how did we get this formula? We are just dividing this curve into many straight lines. These straight lines, because they are very small, they will be like tangents. Okay, so if you add the length of each and every tangent over here, you will get the arc length. I hope that is clear. Okay, and also what do we have? We have something that looks like this: arc length function. Okay, the arc length function, we usually write it like this: 0 to t. It is the same thing, r dash u du. Okay, don't worry. Okay, when we are doing the exercises, you will understand how to calculate that. Okay, so now we have found the tangent vector, the unit tangent. Now all we need is the curvature. How are we going to find the curvature in terms of the derivatives? You are seeing over here, everywhere derivatives are involved. Okay, similarly the curvature we can find it in terms of the derivative. Okay, I will write it over here, curvature. The curvature, it's denoted by kappa. Okay, we have two formulas for this one. You can use any two. It is t dash t magnitude upon r dash t, or you can use another formula, which is, okay, we have another formula for this one, r dash t cross r double dash t by r dash t cube. Okay, r dash t cross r double dash t divided by r dash t cube. Okay, so you can either use this formula or this one. Again, more detailed explanation for this one will be given in another video. Okay, but now what we will do, I will just do one exercises. How are we going to calculate all of these? Okay, so let's see. Okay, so the question is, find the tangent, find the unit tangent unit normal and arc length. Okay, curvature. Okay, when t is equal to 1. Okay, number 2, the arc length function, the arc length from t equal to 0 to t equal to 1. And number 3, the arc length function. Okay, for the curve, okay, let us make it very simple. 1, okay, sine t cos t. Okay, so this one is a very simple exercise. Okay, as you will see, solution. Okay, so if we have to do this one, first of all we will have to find the position vector. So the position vector, it is just 1i, which is I, plus sine tj plus cos tk. Next, what we will do, we will also need r dash t. R dash t will be, okay, just differentiate this one with respect to t. This one is constant, so it will be 0. Differentiation of sine t will give you cos t. Differentiation of cos t will give you minus sine t. Okay, so this one will be r dash t. Okay, so now let us just find the unit tangent vector. Okay, so number 1, unit tangent vector is given by this one, which is r dash t divided by its magnitude. Okay, so the r dash t is cos tj minus sine tk. The magnitude of this one, okay, the magnitude of this will be 0 square plus cos square t plus sine square t. Okay, cos square plus sine square will give you 1. So after calculating this one, you will be having the part t, okay, will be square root of 1. Okay, so it will be cos dj minus sine d. Okay, so this is what we are having, and this one is the unit tangent vector. Okay, but if you see the question, we have to find it when t is equal to 1. When t equal to 1, okay, then you will be having t1. It will be cos 1j minus sine 1. Okay, so this one will be the answer, cos 1j minus sine 1k. Okay, we can leave it like this. So this is the answer. Now we will find the unit normal vector. Okay, now we will find the unit normal vector. Okay, unit normal vector. Okay, if you take a look at the formula, it's given by nt equal t dash t divided by magnitude t dash t. Okay, so this is the formula for the unit normal vector. So now we just have to find t dash t. So tt, it's like this. Now tt, it's equal to cos tj minus sine tk. Tj minus sine tk. So now we have to differentiate it. T dash t. Differentiation of course will give you minus sine. Differentiation of sine will give you cos. Okay, and magnitude, also you can find this magnitude t dash t. Again will be square root, okay, sine square plus cos square t. Okay, which is 1. Therefore nt, okay, which is a unit normal vector, it's equal to, okay, t dash t, which is minus sine t j minus cos tk divided by 1, so it will be this one. Okay, so now let us just find the curvature. Okay, curvature. Okay, let's see the curvature. It's okay, the curvature, it is equal to kappa, it's equal to magnitude t dash t divided by r dash t. Okay, the curvature. Okay, so t dash t, it is 1, right? So magnitude of t dash t, it is 1. So similarly, magnitude of r dash t, we have found out before, it is equal to 1. So the curvature, it's equal to 1. Okay, so this is the required answer for the curvature. Okay. Next, what we have to do, okay, forgot the question. Okay, we have to find the arc length. Arc length from t equal to 0 to t equal to 1. So it will be equal to integration. The limits are from 0 to 1. 0 to 1. Magnitude r dash t. Cos tj minus sine tk. So it will be r dash t, it's equal to 1, right? Magnitude of r dash t, it's equal to 1, because if you remember, rt, it was equal to 1i plus sine tj plus cos dk. Okay, so r dash t, if you remember, we had calculated that it's equal to cos dj minus sine dk. So the magnitude of this one, it will be equal to 1 dt. Okay, magnitude will be cos square plus sine square, which is equal to 1. Again, the limits from 0 to 1. Okay, so sorry. This one is 1. Okay, so for the limits, integration dt will give you t 0 to 1. So the arc length will be equal to 1. Okay, what about the arc length function? Okay, the arc length function will be equal to 0 to t r dash u du. So how will we do this? It will be 0 to t r dash u. Okay, so over here r dash t is cos dj minus sine dk. So r dash u will be magnitude cos uj minus sine uk. How did I get this one? I got this one just by replacing t by u, because over here it's r dash t, but we need r dash u. Okay, so it will be du. Will be 0 to t. Magnitude of this one, it's equal to 1 again. So it will be 1 du. So it will be equal to u. The limits are from 0 to t. So overall it will be equal to t. Okay, so this one will be the arc length function. I hope that is clear. Okay, so this is the final answer that we want to find. Okay, so it's a very simple exercise. Okay, what I want you to do, you can try this exercise on your own. Again, find all those things. Okay, but when the curve, okay, find the tangent normal arc length function from 0 to 1. Okay, and the arc length, find it when the curve is, okay, let's make it, again, it's still easy, 2t and maybe 3t squared. Okay, just try this one on your own. Okay, let us see. Until next time.